All right, so today we are going to talk about dimensions and how to put dimensions onto drawings. Because obviously, remember that we're making these drawings to hand them over to people to manufacture parts, right? And so we want to put dimensions on there that are very clear and to let them know what it is, how big the pieces are that they need to create. And we want to put those dimensions on there written out instead of letting them measure, because that just causes all kinds of problems. So this is what it would look like, right? So we have our parts. Here would be our three projections or orthographic projections. We always dimension on the orthographic projection. We never dimension on the pictorial, except if I give you something for the exam to do it, that's slightly different, just so you know what to draw. But again, what we want to do is we want to give the exact size of an object. All right, so here we have the little piece that we used last week to learn how to do circles in the isometric view. And here are all the different types of dimensions on it. These dimensions need to be concise, right? I don't want to have a whole bunch of extra text, because the more text there is, the easier it is to get something lost. They need to be clear, right? I have to be able to read them without any issues, which means they need to be big enough, right? There can't be any other kind of clutter around them. And all the information that I could possibly need needs to be included in these dimensions, right? So here we have, for instance, right, the circle here tells me that it has a diameter of 4 and a depth of 1. Right? If we look over here, we can see that it doesn't go all the way through. Right? So that's why it had a depth of 1. I'm told, like, what the arc is here, how big the arc is, how far the center point is from this edge, how far the cylinder goes out, all these kind of things, all very clear, all very precise. Right? So again, if I wanted to make this part, all the dimensions here need to be on there. And nothing should be left to be measured. Right? So I don't ever want to see anybody pull out a ruler and start measuring stuff just because it might not be to scale, right? I might not be drawing something at a 1-to-1 scale, so that makes it difficult. Also, we have to remember that, let's say we create this on my computer here, and then I put it in a PDF and print it out. All of a sudden, it's no longer at the scale that I think it is, right? Because my computer scaled down a little bit to fit it onto a PDF on a single piece of paper, for instance, right? So that's, if we have the numbers on there, then it doesn't matter how much they get squished together or pulled apart, those numbers are still there, right? That's why we never want to have to measure anything on any of these drawings. Let's go through the different types of lines that we have on our dimensions. We'll start out here. So this, the long line with the 2 arrows at their ends, that's what we call a dimension line. Right? It tells us what the extent of the part is that we want to dimension. These lines here that have this kind of an arrow on one end and then this little kink in it is what we call a leader line that points from a note to an object. Then we have these thinner lines here. Those are what we call extension lines. They're there to show very clearly what size we're dimensioning, right? So here, for instance, it would be the edge all the way to the center point, right? That would be its dimension. Here, it was from this edge to the center point. Here, it'd be from the side to the bottom. Although we don't really like to do this here, but we don't want the dimension right against a visible line. We probably want to have that somewhere over here. But again, these are the 3 types of lines that we have: dimension line, leader line, and extension line. Those are the three types. Right, and we can see them in different places, right? So here's a dimension line, here's a dimension line, another dimension line. We have a leader line here and a leader line there, and then extension lines all over the place. Now, if we look at detail of our dimension line, right, then we have just the dimension line itself. That's the long line that goes across. It has 2 arrows on each end, and then it has the feature size in the middle. So we want to have this more or less in the center between these two, between the 2 extension lines. And we don't want to write it through the line. We want to kind of leave a little blank space where it can put this number. The arrows need to be visible, but not huge, right? So arrows obviously are a little bit tricky when we do this by hand because we're not going to use a straight edge to do this little arrow. That would be too much effort, so you have to be a little careful with how you do the extension lines and the dimension lines. However, we do want to do with a straight edge, right? Those need to be nice and neat. So these were details of the dimension lines. If we look at details of the extension line, right? It's a little thinner than our dimension line, and it should not connect to the part that we're trying to measure, right? So in your case, there's always a visible gap between the piece and the extension line. And the reason for that is that we don't want to mistake this extension line to be any kind of visible line of our object, right? That's why we always have these slight gaps in between here as well, right? We don't want to get confused between the center line and the extension line. That's why we have a gap there. And for the leader lines, right, we have has an arrow on one end, as I already said, and that arrow points to the object that it's that we're trying to point at. In this case, this leader line points at this arc, right? So it ends on the arc. There's no gap there. It goes straight to the arc, right? And if it's pointing at something that is a circular shape, like here, like this arc, or a full circle that we see right here, then this line, this leader line, is supposed to point at the center of that arc. Sorry, because that helps us understand what we're looking at. So it is made up out of the arrow and the line itself. And then at the end of this leader line, it always goes into the horizontal. So the last piece is always horizontal, it's one kink. And then we add the whatever note we want to have on this leader line at the end. Now the angle of this leader line towards the horizontal, we want to have this to be somewhere between 30 and 60 degrees. Ideally, we want to have it right around 45 degrees because it makes it nice and easy to see. We can have it coming from the top. We can have it coming from the bottom. Of course, just like here, we can have it coming from the other side. If possible, we want to have it come from the top. But again, it's not always possible. Sometimes it comes from the bottom. Now here, the types of different dimensions that we can have. Over here, the most common one that we'll see is the linear distance, right? So how far is this point from that point? In this case, it's 10 units, probably 10 millimeters, 10 inches is pretty big. Then we have angles in here. We don't see all that many angles, but sometimes we have some. And then last, whenever we have a leader line, then we have a note. In this case, the note says that the circle that it's pointing at has a dimension, has a diameter of 5. That's the different types of dimensions that we have. 3 different types: linear, angle, and note. All right, let's go through this and let's see if we can guess what types of lines we have. All right, so what's the line that my arrow is pointing to? What type of line is this? Nothing to do with dimensions. We go think back. What is it that we call these types of lines? But those are what we call the visible lines. Right? That's the things that we see when we do our drawing. How about the little dashed lines? What do we call those? I know we're not in class, but nonetheless, we can have some participation here. What do we call the little dashed lines? They're not visible, but they're hidden. What are the hidden lines? Right? Those are the visible lines we use for both isometric and for orthographic, and the hidden lines we only use in orthographic. How about these lines here? It's crosshair, what we call this. The lines that a lot of you missed on the orthographic projection practice.
Center lines.
Exactly. Very good. I was going to say lines. I know it's late in the afternoon, but it's only Monday, so you have to have a little energy. That's our center line, right? Now this line here, what do we have there? What do we call that? It's one that we just learned. So we call that a leader line, right? Because it leads points to the circle. How about this one?
Dimension line.
Dimension line, exactly. And then the small ones here, the same one there. What do we call those? Those are the extension lines, right? They extend our object out to where we can do our measurements. And then what type of dimension is this? We have 3 different types, right? We said we had linear, we had angle, and we had note. This one obviously is an angle, right? Has a little degree sign there, right? So the angular one, this one is linear, right? That's just a distance. And then up here would be a note, right? But the thing here is, because this note is attached to a leader line, this is what we call a local note, right? So it only applies to where this is pointing to, right? That's why it's called a local note. The one over here, that's kind of floating around, that's what we call a global note. This is true for everything, right? So here says, note all holds through, right? That means that all the circles that we see here go all the way through my object, right? So for instance, I could, if I was given the thickness of this, right? If I had another note saying that thickness, whatever, 5 or something, right? Then I could get away with this single view to produce my part, right? But so these are the different types of lines and dimensions that we have. Now let's talk about our linear dimensions, our arrowheads. We have a couple different ones. If at all possible, we want to have our number in between the 2 extension lines, like here, like this 100. Right? Again, about halfway between those 2. Again, when we're doing it by hand, it's not going to be exactly halfway through, but somewhere there. And the number should be centered on this line. Now, if there's not enough space, then sometimes we kind of draw the arrow all the way through and then put the number outside with a little leader line. But this leader line is vertical or horizontal. And if there's even less space, then we just have the number in between the extension lines and the arrows on the outside. Right? Those are our options. But again, if at all possible, we want to have the one where we have the number in between because it's the clearest. It adds the least extra stuff around. Whenever we have text, we want to have it easy to read. It needs to be uniform in size and weight, right? So weight is like the thickness of how we write it. And it needs to be horizontal. Why would we want to have text be horizontal on our drawing? Think about a drawing in front of you, right? Let's say there's text written on there that's vertical, right? Well, we may have to turn the drawing around to be able to read it, right? Now, if you have a small piece of paper, like letter size or something, right? That's not an issue. It's always easy to turn that around. But if you have one of those big drawings, then you'd have to walk halfway around the table to be able to read those notes, right? So that's why we want to have everything be horizontal, so it's easy and clear to read. We want to have everything uniform size and weight, because if there's something that's written bigger or smaller or thicker or thinner, then whoever's reading the drawing is going to assume that you did that on purpose, right? So if there's something that's sorry, if there's something that is like bold and everything else is regular, right? Then they'll think for some reason this needs to be highlighted and there's something special about it. And so we don't want to do that. We want to use only uppercase letters. Again, that's to make it easier to read and clear. Right? Remember that an L might look like an I. The lowercase l and the uppercase I look exactly the same in many font types. So if we know that everything's in uppercase, then we know that's an I and not an L. Of course, the uppercase does not help us with an O and a 0. They still look the same for uppercase. And whenever possible, we want to use symbols instead of text. And the reason why we like to use symbols is because symbols are basically their own language that anybody who does these drawings learns. And so that makes it easier to transfer these drawings between different languages, right? If I write something on there in English and I send it to Costa Rica, then people may or may not be able to read it. Even worse, if I send it to a place that has a different alphabet, right? If somebody does it in Russian and writes using the Russian alphabet, then like we're kind of off. We don't know what to do. Or if they use like Chinese font, right? So that's all those are going to make it difficult. But if we use symbols, then everybody knows what those symbols are. And we'll next go through these symbols. I kind of list them here, so you have one place to go back and look at them. But we'll the next couple slides, we'll go symbol by symbol. Well, we have the diameters, just a circle with the dash through it. That's for a regular circle. If we have a sphere instead of a circle, then put an S in front of it. If we're giving the radius instead of the diameter, then we do a capital R, and the same for the spherical radius. And we'll talk a little bit about when to use a diameter and when to use a radius in a minute. If we put brackets around something, then it's what we call a reference dimension. And a reference dimension really just means that it is not supposed to be used for dimensioning. Right? It's given there to be helpful, to explain something, but it shouldn't have to be used to actually produce a part or something, right? So these are kind of more helpful notes than actual something to measure by. Then this rectangular U shape here is for a counterbore, and we'll talk about what a counterbore is in a little bit. And then the V here is a countersink, and again, I'll explain what a countersink is in a bit. If we have a capital X and a number in front of it, then that just means it needs to be repeated a certain number of times. So in this case, 4 times. Right? So if we had 4 circles next to each other that are all the same, then I can just say 4 times, and I don't have to dimension every single one of them. The advantage, we'll get to why we do that when we talk about it. And then one more important one is this kind of arrow pointing downward. That is the depth, right? So remember, for instance, on the piece that we used to draw the circles, right? I had the little kind of dimple in there, and so that would be, I could just put the symbol of the depth and then a number behind it, and then whoever reads the drawing knows that that little piece is like that hole is supposed to go. I guess we have 1 unit, I think, going in. The rest of them, I guess basically have here for reference that they're not really, we're not going to use them very much, but if you see them, you come back here, you figure out what they are. All right, let's go through each of these symbols in a little more detail. So the first one is when we look about circles and arcs. I have a couple of different examples here. So if I have a full circle, then I use the diameter. Let's see, here's diameter 5. If I only have an arc right here, well, the next one, right? I don't have the full circle. If I only have a partial circle, then I'll always use the radius. And so be very careful when you do your drawings to not get confused between diameter and radius. Right? Diameter is all the way across, and diameter is only from the center to the circle. Also, you'll see something like this on the right, the last one, the third one, right, where something looks like a rectangle, but it has a center line and then a diameter given. Right? Although this looks like a linear dimension, this is actually a diameter, right? And so we give this for any cylinder that we have. We'll always give it as kind of in this what we call the rectangular view. But again, because we see that there's a center line, we know it has to be cylinder, and then this gives us what the diameter of the cylinder is. We talked about the kind of the depth symbol here, right? So if we had something that a front view, for instance, that looks like this, right? Then I can say this would be a hole with a diameter of 5. And it goes 10 millimeters in, for instance, right? So if we look from the side view, right, then we can see it goes 10 millimeters into my object here. I don't have no idea how long my object is, but we know it goes 10 millimeters in. And then often we'll have this kind of cone shape at the end of our holes. And that's just because the way that we create our holes, right? The holes are going to be drilled into there. And so this cone shape here is basically the drill bit, right? The front of the drill bit where it kind of goes cone shape or triangular shape, depending on the drill. So that'd be one way. Now, sometimes if the hole is going to go all the way through, right, then I can put THRU on there. That's not the best way of spelling through, but that's the accepted way on these drawings, right? That just means that my hole goes all the way through. Now, if I'm given the side view and there's no obstruction and it looks like it's going all the way through, then I don't have to put THRU there. I can just do diameter 5 and it is implied that the hole goes all the way through. But if there's no other information given, then I should say that it's going all the way through. Otherwise, it could be something like this, right, where it has a depth to it. Now, center marks, right? We talked about center lines and where they intersect, that's the center mark. We don't always have to put them, right? So for our orthographic drawings that we did, I wanted you to put them up in the corners. They're not 100% necessary there, right? If you remember that kind of shape that had the rounded off corners. So if you look at the first one here, so we're given the radius, and if we were given the rest of the dimensions here of the sides, then we knew exactly where this radius have to be, because we could draw in the rest of our circle here, right? So we would know where the center line of it is just based on these two, where the two lines come in, right? So that's why we wouldn't have to have a center line there, because we know where the circle goes even if we don't have the center point. Now, in this one, we do have to have a center point, but we only have to dimension the height here. We wouldn't have to dimension anything in this direction, because we know that this is, if it ends here in this line, then this distance here has to be a radius of a distance of 6, right? Just because otherwise it wouldn't end here correctly, right? It would either come in at an angle or go like this, right? So if we see it comes in straight, then it's the correct one. Up and down, we don't know, right? So that's why we have to see where this is, because we don't know what the angle is. Of course, we could have been given the angle here, and then we wouldn't need to know where the center point is. But measuring angles is usually more difficult than measuring lengths, so we usually have lengths instead of angles whenever possible. And of course, this case here is just taking it one step further. Because we have an angled line here and an angled line there, we have to dimension exactly where the center point is. Otherwise, we wouldn't be able to find it out. All right, so these would be how we dimension center marks. If we have spheres, obviously we'd have to put the little S in front of it, right? So this would be just a ball that has a diameter of 5. If we have something like here, where we have basically like a rod, kind of like the end of my pen here, right? That has a little end of sphere on it. I mean, it's a very flat sphere. But if we have anything like that, right, then we have to give what the sphere is, and we'd have to say where the center of that sphere is. You wouldn't otherwise know, right? This could be further in or further out, and then this shape would be just more or less round. These are spheres. We don't do a whole lot about with spheres, but a lot of circles. All right, now very important, the difference between the rectangular and the circular view. So I hope by now you have a little bit of an idea of kind of seeing this shape, right? So if we see the front view and the side view in this case, then we can see that from the front view, you can see there's a circle here and a circle there. But we can't really say anything, we can't really understand what it is that these circles are, right? Are these circles holes or are those cylinders? Right? But if we look at the side view, then we see the top one is a cylinder and the bottom one is a hole, right? We can see kind of the extent of this hole being there, the dashed lines, right? So that would be helpful for us, right? So we can see this. Now, in order to make things more clear and avoid mistakes wherever possible, there's a convention that says that circles and holes only get dimensioned in what we call the circular view, right? Where this shape looks like a circle, right? So this hole here looks like a circle in this view, but looks like a rectangle in this view, right? So because it's a hole, it gets dimensioned on where it's a circle. Cylinders, so stuff that circles that are coming out of my object, they get dimensioned in the rectangular view, right? So it looks like a circle here, looks like a rectangle here. Well, we dimension it on the rectangle, right? So that's the rectangular view, and that's the circular view. Right? Just went through these, right? And the idea of why we do that is, again, we want to avoid mistakes wherever possible, right? So if I am somebody who knows how to read these drawings, right? I know this convention, then I don't need to see anything else, right? I see here, this is a circle that's being dimensioned on the circular view, so I know that has to be a hole. If I just look at the side view, right, for this one, I know this has to be a cylinder because it's being dimensioned in the rectangular view, right? So this is something that's very important. This is something where this is something you'll have to take into account when you do your dimensioning, both for your homework and then on the exam, right? So be careful of these. We also have the idea of this repetitive feature, right? It's at 4 times of something. So here we would have this square piece that has 4 holes in it, right? And all the holes are dimensioned where they are, but instead of putting the diameter on each of those, I can just say 4 times and then the diameter, and that means I know that the diameter of each of these 4 holes is going to be 5. Now, very important, there's no space between the 4 and the x, but there is a space between the x and the diameter symbol, right? Or whatever else is coming after it, right? So if I had 8 times a length of 5 or something, right, then I had 8x blank and then 5, right? So it's very important that we don't put those together, because if we do, then it has a different meaning, right? We'll see in a little bit. It's a different thing to dimension if there's no blank there. So there's a lot of details in this. Now, maybe one more thing, right? So we said that we don't want to have any more views than we have to have, right? So in this case, we could get away with just a single view, right? Because it gives us the overall outline, it gives us all the holes, and it says that all holes go all the way through, and that the whole part has a thickness of 2, right? So if I get these notes and there's no other views to it, then I should assume that everything stays the same over the entire thickness, right? If there are other things going on through the thickness, then I would have to have another view to do it, right? So in this case, it's great we can get away with a single view, and with that, we can move on without having to worry too much. Again, the fewer views that we can do, the better, because the fewer mistakes that we likely have. So that was 4 circles that are all next to each other. We also do this often for the spacing out of features, right? So here we have 5 circles that are spaced out nice and evenly. So we can just say that these distances here would be 4 times 10. And now the reference kind of comes into play, right? That says, as reference, the overall length here should be 40, 4 times 10. Also, it gives the reference here of being 10, right? So that helps us to understand what the 4 times 10 means. In this case, it's the distance between these circles. Even if we weren't given that, then we should be able to figure that one out, right? Of course, we have another up here where we say 5 times the diameter of 8. Each of these circles has the same diameter. Just because they have the same spacing doesn't mean they would have to have the same diameter, right? We could have something that has a big spacing and the first circle is big, and then each smaller, gets smaller and smaller as we go along, right? Then we have to specify that as we go along. Now we come to the counter board. The counter board, I'm pretty sure you've all seen them before. basically what it is, if this were a cut through our piece, right, then we can see that we have the shaft where our bolt is supposed to go into, and then there's an extra cutout here. And that extra cutout, of course, is for the head of the screw that we're putting in here. Right. So if this is something like a chair or a piece of furniture or something like that, right, then we don't want to have the bolt sticking out, because, like, we'll be sitting on that chair, and if each bolt is sticking out, then it's going to make it very uncomfortable. Right? We're going to have it poking into our butt. We don't want to have that happen, of course. Right? Those are those counter bores. Now, the way that they will look like in a technical drawing is like this, right? So we'll have our leader line, and it will say a diameter of 3. I'm sorry, that would be the diameter of the overall hole, right? The actual one that goes through. It will say it has a counter bore. That's this rectangular U shape here, that pan kind of looking thing. And then it gives what the diameter of the counter bore is. In this case, has a counter bore of diameter 8. Right? So the diameter here, this distance, would be 8. And then the depth that is given is the depth of the counter bore. This would be how deep this counter bore goes in. Right? Basically, how big do I think the heads of the screws are they going to be, so that they have to fit in there, of course. So that would be the idea of a counter bore. Now, the other one that we have is the counter sink, right? We have some screws that don't go, where the heads aren't flat, but they have their angle, right? Usually when we use wood screws, we have these angled screws, so we can turn them all the way in, right? And to do that, we want to cut out a little space. If it's not wood, it's metal, right? Especially then we want to cut out a space so that that cone shape can fit into there, right? That's the thing what we do there. And it looks very similar, right? It looks, again, like a bullseye kind of a thing, where the outside line would be the outside circle from here to here at the top. And it will say what the diameter is, in this case, the diameter 8. And then it will say this angle here. And this angle, basically what it is if you take these lines, actually, let me see if, let me draw here real quick. Right, if I take this line and I extend it, and I take this line and extend it, and this angle between them is what we see over here. That's that angle. Right, in this case, it's 90. We'll have some that are 60, that are 30, right? That just means that cone is flatter or steeper. And that depends very much on what the screw is that you're using, right? You want, of course, want to have a screw that fits into it. You don't want to have a screw that's super flat and, a cone that's super, or like a counter sink that's super narrow, right? Otherwise that would work. The other thing that I want to point out here, as I said before, it is important where you put the blanks, right? So you see here we have X again, but now the number in front of it is not right on it, right? It has a blank in between. And this means now that we have a counter bore with an outer radius of 8 and an angle of 90 degrees, right? It's not that we have 8 times the angle of 90 degrees, right? There's no 8 parts that we're pointing to. So this is a counter sink. And then a chamfer. I bet you've all seen those at some point or another, right? The chamfer basically is if you had any kind of a rod shape, and then the edge is kind of softened off, right? It's flat instead of just having a sharp corner, kind of has some kind of a angled surface instead. And there's mainly 2 reasons to do that. Number one is that it creates edges that are not as sharp, right? So if you machine this out of metal, and you have a very sharp corner, then that edge can be very sharp, and can be, if you're assembling stuff, could cut your fingers, for instance. But more importantly, having this kind of chamfer helps to get, usually these are bolts, right? Get into their respective holes, right? If it kind of, it gives you a little bit of a guide, right? So if you don't hit the hole exactly, then it will slide you into where you want to be. If this were just a straight hole, then you'd have to line it up perfectly to get it. Just makes it a little easier to move your bolt into the respective hole. Now, there's many different ways that we can specify this. There's the one here that says 2 times 45 degrees, right? And what that means is 2 is this distance here, right? So from the original diameter to the smaller diameter, this distance is 2, and the angle that this line has here, that angle is 45 degrees. So that's one way to describe it. Another one is to say it's 2 by 2. That means this distance here is 2, and this distance here is 2, right? That and that both are 2. Of course, is the same as saying one is 45-degree angle. And then the last is to specify it all the way out, right? To give this width and then the angle there. Usually we wouldn't use this unless this is something, very, very specific, very unusual, then we might actually put the angles here. Otherwise, it's just easier to write like this, right? People know what this means, and it's a lot more concise than having this whole full dimensioning part on it. All right, these are chamfers. And then I think the next part I have here is just stepping through the actual dimensioning of a part, right? And not today, but on Wednesday, I'll let you sit down and do your own dimensions. Just today, I don't want to go through all dimensions in one day because it's a lot of information, but we'll go through more on Wednesday, and then you can do your own dimensions. But let's just kind of do a quick one here. All right, so let's start with our circle here. All right, so if we wanted to dimension the circle, then of course we know it's a hole, right, from here. And I hope you recognize this part. That's what you have drawn or need to draw today. So this is a hole, right? If it's a hole, we want to dimension it in this circular view. And in our case, this is the only place of our 3 views where this hole is a circle, right? If we look over here, it's a rectangle. If we look over here, it's also a rectangle, right? So we have to dimension the circle over here. So we put it right there. Pull a leader line, pull it out, a diameter of 6. All right, so now we know what the size is, but we also want to know where it is, right? And so we have to dimension that, the location, right? So we can say the center of the circle here is 16 millimeters from this end, and then 6 millimeters in from the top, right? Okay, that's good. That gives us the exact location of this point, right? So this hole is now completely defined. So that's good. Next thing we want to define is this arc, right? We have our arc right here. Now we already know where the center point is, but it's the same center point as the circle. So all we have to do is give it its dimension, right? So we can say this is has a radius of 6, right? Again, now we're doing radii because this is not a full circle, right? Any arc is a radius, any circle is a diameter. Now we could, based on this, get rid of the top number here, the 6, right? Because if the circle and the arc have the same center point, then we know that it has to be 6 millimeters from this edge, right? The center point has to be 6 millimeters from this edge because the radius is 6, right? The radius is 6. So from here to there has to be 6 millimeters. From here to there has to be 6 millimeters. So it's a half circle. So we could take that away, and sometimes we do. If you put it on, I'm not going to complain about it. Sometimes it's a little helpful. All right. So with that, we have our arc and our circle well defined. So let's go around and do some simple ones, right? So if we want to have the thickness here, right? This part, we can see this thickness here, and we can see it here. On Wednesday, we'll learn one very important rule is that we never want to dimension hidden lines, right? If you wanted to say, oh, this is the thickness of 2, we can put the kind of an arrow on here and say this is 2. We never want to do that though. We always want to have it at visible lines, like down here. The reason why we don't want to dimension anything on hidden lines, because as the name says, right, those lines are hidden on my actual object. So if somebody is taking the object that was produced and wants to do a quality assurance, right, and they want to measure something, well, they can't measure from an edge to a hidden line because they can't see it, right? So we always want to dimension it on something that we can see. So that would be this part here. We can do the thickness here and has the same thing, right? We can see it here and we can see it there, but we only want to dimension it here because that's the visible one. We also never want to dimension the same thing twice. This came out a little wrong, right? It should go all the way down to the bottom, of course. So that would be those two parts. Now we can go ahead and dimension our cylinder, right? This is the cylinder that comes out at the end. So we can do that. Now it is a cylinder, right? So if it's a cylinder, we only want to dimension it in the rectangular view, right? So in our case, the cylinder shows up as a rectangle in two places. It shows up here and it shows up here. And so now it's really up to us where we want to dimension it. There's no rule that you can do it in one or the other, but in general, we want to have dimensions kind of grouped together as much as possible. So that's often what drives it. In this case here, we say that this dimension is 4. So we dimensioned up here. And then of course, we also need to know how far this comes out. Also, so we'll dimension it right there. And the reasons why we're dimensioning it up here and not down there, might be the same difference, is that we already have a nice length here. And we also already have the dimension of the diameter here, so we kind of want to kind of group those together as much as possible. All right, so then with that, the only thing that's left for us to dimension is where this, or almost the last thing, I guess, is where this center point sits, right? And we can say, oh, 6 from one side here, and 4 from the bottom, right? That gives us the exact spot, and that then means we know where to put our cylinder. Last piece that we're missing is the height of this overall piece, right? We could dimension it here, but it's kind of a little messy because the cylinder is sticking out into it, so it's better to dimension over here. It's easier to see. So we could either dimension it all the way here, or we can say, well, we already have part of it given, so we'll just give it the rest. That'd be 6. And with that, we have pretty much everything measured. The only thing we don't have, or we do have, is this one, right? Remember that if we know how far this distance is, right? We know this is 6 and 6, then we know this has to be 12, right? So we don't have to give it a specific dimension. We don't have to put another 6 down here or a 12 here or something, because this side of our object already tells us what this distance is. So with that, we have our piece fully dimensioned, right? So with this, we could now go in and have somebody create this part for us. Like, go down to the machine shop and punch this into your computer, and this is all you need to know to get exactly this part. Questions about these dimensions? No, again, on Wednesday, I'll let you practice drawing them yourself. It's just that there's another set of rules that we kind of have to obey, and doing them all in one day is a lot of information all at once. And if I do that, then there's no more time to practice anything. So I like to do half of it in one day, and then we'll practice a little more isometric drawings. And then on Wednesday, we'll do the second half, and then practice the dimensions. All right, I think that is there anything else? Oh, this length we already have. I forgot to tell you that, right? Of course, we have from this edge to the center point, and then because of the radius, we know how far this point has to be, right? So we have all this together. Now, this might look a little confusing, but especially once we get to drawing using Inventor, you'll see that it's real. You'll see these little tricks pop up all the time, and you'll learn how to use them easily. So that is our fully dimensioned part. Let's see. Yeah, with that, we now come to the practice part of the day. So I have 2 more isometric drawings for you to do. There's the one here, where you can see that we have has to be a cylinder, right? Because it's dimensioned in the rectangular view, and this has to be a hole because it's dimensioned in the circular view, right? So we can see our hole here, and we can see our cylinder here, right? And otherwise, this is just an L with an arc on it. So basically what this is just getting you to practice drawing circles. That is one. And then the other one is this one here. And this is a little bit more of a complex looking shape, especially this part up here, right? Because it doesn't have any dimensions on it. If it doesn't have any dimensions on it, that means that we have to reconstruct it, right? We're given that this is at an angle here. We're given where this point is. We're given where that point is. So basically, it looks, if you look from the top, right, it looks like a rectangle that has the front corner cut out, basically cut off. Right? So that's what we want to do. So these are the two that you have to do today. What I would like you to do today are due to be finished on Wednesday. Let me open them up on Blackboard. Forgot that available beforehand. So that would be 5 and 6. They are now available. So if you could grab those and start drawing those, and if you have any questions, then I'm more than happy